Up now we have Lucy Parker, who's going to talk to us about the seL4 device driver framework. Take it away.
Hello. So my name's Lucy. I'm a fourth year undergraduate student at the University of New South Wales in Sydney. I'm one of Gernot's students at the Trustworthy Systems group, and today I'll be talking about the research and development I've done on the seL4 device driver framework. So first off, a quick recap. What actually is the device driver framework? Well, as you all know, by design, seL4 already prescribes device drivers to run as user-level programs. This, of course, has the advantage of significantly reducing the trusted computing base and also providing strong fault containment for what's historically been very bug-prone code. However, without careful design, it has the potential to degrade performance as the system requires significantly more context switches. The sDDF aims to rectify this by providing interfaces, protocols, as well as example components and drivers typically found in a high-performing system. The design enables formal reasoning. We're beginning to explore the verification story, but it already demonstrates performance better than Linux in a simple networking-based system. So one of the main design goals of the framework is to prioritize a strong separation of concerns. So this means that the driver runs as a library, runs as an isolated component rather than a library inside an application, and then communicates with other components in the framework, which I'll get to shortly. So this means that the driver is inherently event-driven. It's either reacting to a hardware event or a request from a server. So for example, you could have a file system that makes a request to a block device to write something back to disk. And they all communicate asynchronously. Oh no. This is my nightmare. Okay, so they all communicate asynchronously in shared memory and using seL4 notifications. It is currently very much focused on networking systems, but we have other drivers in the works, namely timer, serial. We're designing the storage interfaces, as well as I2C and running driver virtual machines with drivers and having them communicate via the same transport layer as well. And it's currently all implemented on top of the seL4 microkit, or previously coined the core platform. So the driver model utilizes three distinct memory regions. The hardware takes instructions from its registers, and then, or rather the metadata region, and then reads and writes data to a specific location via direct memory access. Now this data region can also be mapped into other components' address spaces, which enables a zero-copy interface. And then these components communicate with the driver via the control region. So a server can issue transmit requests, receive information on newly received data, and then likewise in reverse for the driver. Now in a networking-focused system, the driver doesn't actually need to access the data. It's simply translating a device class protocol, i.e. the control region, into a hardware-dependent protocol, i.e. the metadata region. So we can further reduce the trust we place in the driver by completely avoiding mapping this data region into the driver's address space. And then we simply use notifications to signal updates to the shared memory regions. So if the server makes a request to transmit, it will then signal the driver of this update in the control region. Likewise, this could come from the device from an interrupt, which of course is mapped onto an seL4 notification. Now the transport layer or control region, it consists of lock-free bounded ring buffer queues. And these queues are single producer, single consumer. Components on either side are also only single-threaded, and this is a very intentional simplification. And then we use 2 queues per direction, much like the VirIO interface, and these queues simply keep track of the buffers in the shared data region. So for example, on the transmit path, we have the transmit used queue, which keeps track of buffers ready to be transmitted, and then the transmit free queue, which keeps track of buffers free and ready to be reused again. And then for larger systems with multiple components, we have a control region between each of these components. For example, if we wanted to have multiple client applications sharing the device. So here I have a simple multiplexer design whose sole concern is sharing the NIC. For this reason, we actually separated out the receive and transmit multiplexers into separate components, as there's no need for these paths to cross. The receive multiplexer is implemented at layer 1. So this means that clients have a virtualized MAC address, and the device runs in promiscuous mode to get the extra traffic. So we could have implemented it at layer 2 or layer 3. But then we'd be restricting clients to a specific set of protocols or ports. However, with a layer 1 implementation, it brings about the problem of, well, how do you handle broadcast traffic? So for that, I have a simple ARP component, which stands for the Address Resolution Protocol. So it currently, clients register their IPv4 address with this ARP component, which then responds to ARP packets on behalf of the client applications. It is currently limited to just this particular protocol, but there's no reason why you couldn't put a DHCP server in there as well. Now you might have noticed there's an extra copy component on the receive path. So this copy component is purely responsible for copying data from the shared data region into the client's own address space. So this prevents clients from having the ability to access each other's data. It's not strictly necessary on the transmit path, as clients can have their own separate transmit data regions that the NIC can access directly. However, there's some designs where it might make sense, and I'll get to that at the end of the talk. And then as far as policies, on the receive path, the only policy that really makes sense is a FIFO policy. However, when the client's received use queues become full, the multiplex will throw out any incoming traffic for those clients. On the transmit path, there's a few different policies that might potentially make sense. And rather than coming up with some generic policy that tries to cater to all possible use cases, instead I've implemented multiple simple multiplexers that each implement a particular policy, and then you take your multiplexer for your specific use case. This keeps them very simple, and should the need arise, you can even swap them out at runtime, or even combine them. So the policies I've implemented are round robin, priority-based, and throughput limiting. But what we've also found is that we can limit the queue sizes of the clients to implement policy as well. So this limits the throughput available to clients. Okay, so you might be wondering, we've added all these extra components since last year. Doesn't that just degrade performance? So for a simple benchmark, I have a single client echo server, which uses the LWIP network stack to process the traffic. And then this communicates with the copy component, the two multiplexers, and the driver. Then we used IP Bench, which is an open source load distributor split across 4 separate x86 machines. They send UDP packets of a specified byte size to the target seL4 machine, which then echoes them back, and IP Bench will count the number of successful replies to determine the overall achieved throughput, as well as the latencies of the packets. And then we also ran an idle thread in the background to count the idle cycles to determine the overall CPU utilization of the system. And then I compared this directly to a typical Linux setup. So the Linux I used was 6.1.1. So this is with an in-kernel IP stack and driver, of course, and then a user space echo client. Again, an idle thread to determine the CPU load. This was all running on the same hardware. It was the 4-core ARM board, the IMX8MM. But for these following benchmarks, everything's pinned to a single core. So here's the performance comparison of seL4 versus Linux. So this shows the requested throughput against the achieved throughput, as well as the CPU utilization of both systems. So seL4 in green, if you have a look at the solid line, you can see that the system achieves wire speed. It doesn't quite look like a gigabit at the end there, but this, of course, if you're running on a hardware with 1 gigabit NIC, you're limited to only 958 megabits per second due to the Ethernet headers. You can compare that to the solid yellow line, which is Linux. You can see that that system actually maxes out at about 650 megabits per second. If you look at the dotted lines for the CPU load, the reason why Linux maxes out is because the CPU becomes overloaded, compared to seL4, which is actually just shy of 80% load at wire speed. So this is pretty cool. But the multiplexers don't do any multiplexing because they're just servicing a single client. So I have some multi-client performance benchmarks as well. So here I've implemented all of the components shown in the diagram with the following priority assignments. So the driver runs at highest priority, followed by the multiplexers, and then the copiers for each client run at equal priority, and then the clients at lowest priority themselves. So this means that as soon as packets are ready to be transmitted, the appropriate components are invoked to transmit them. Sorry, the ARP component's also there, but you can imagine that this has very minimal traffic. And then to test it, I ran 2 separate IP bench instances on separate clusters of these x86 boxes, and they sent UDP packets to their respective clients at the same time. Now, as far as policy, because the clients are running at lower priority to the transmit multiplexer, it didn't make sense to implement a complex policy in the multiplexer when we know if client A makes a request to transmit, the multiplexer will run straight away. So there's no point looking in client B's queues because it probably hasn't had a chance to run yet. And rather than the multiplexer concerning itself of if a client would like to run and when, or if it has yet, I instead had the multiplexer just react to the client that signaled it. And then we rely on the kernel scheduler to ensure fairness between the client applications. So here is the requested throughput per client against the achieved throughput. So you can double this for the total load on the system at a time. So you can see that both clients achieve their requested load, and CPU load is just a fraction higher than in the single client case. What if we wanted to have clients running at different priorities? So for this next benchmark, the same components, but I had client A, the copier of client A running higher priority than client A, followed by the copier of client B and client B. Now, as the sDDF contains a single pool of shared buffers on the receive path up until those copy components, a low priority client actually has the potential to starve a higher priority client because it'll monopolize all these shared buffers in its receive used queue, and then there'll be a limited availability of free buffers for the higher priority client. So in order to combat this, I limited the low priority client's queues to just 16 on the receive path. So the original size was 512. So this limits the receive throughput available to the low priority client. And here is the performance. So you can see client A, as expected, achieves its requested load, and client B is just shy of 400 megabits per second. But I'll say that this is with the exact same multiplexer policy as I showed in the equal priority case. So can we limit throughput even further? The same benchmark again, but I also limited the transmit queues to just 16 as well. And you can see that now client B is stuck at around 200 megabits per second. CPU load is even lower. So you can see that without implementing any explicit policy in code, we've actually implemented a policy on the system by just manipulating the queue sizes. This, of course, isn't strictly necessary, so just to show you that it works, I implemented a simple bandwidth limited policy in the multiplexer, which limited client B for this example to just 100 megabits per second using a time window of 1 millisecond. So if client B makes a request that would mean it exceeds this limit, the multiplexer waits for a timeout from the timer driver before servicing these requests. And this works quite well. So client A achieves its requested load. Client B, as expected, is stuck at 100 megabits per second. CPU load is even lower. So how does it all work on multi-core? So to just start off with, I have a simple benchmark comparing the single client case against Linux. So Linux again in yellow and seL4 in green. You can see the Linux system still maxes out at, or it gets to 800 megabits per second, whereas the seL4 based system, of course, still achieves highest speed. Interestingly, Linux uses 1.5 cores for this. So for the configuration, I pinned the Echo server on Linux to a single core, and then I had the kernel scheduler work out the rest. But this core with the Echo server was actually the bottleneck. Now you compare this to the seL4 based system. I've got 2 benchmarks there. So the first one is the dark green, running everything on a single core but using the SMP kernel. So this shows the overhead of system calls when using this configuration. I should have had the normal single core case on that graph, but it's roughly 10 to 12%. And then you add another 10% when you add the overhead of cross-call communication as well. But it doesn't really make sense to use multiple cores if you can do it in one. So I came up with a simple benchmark where it might make more sense. So here is a multi-client single core case where the clients can't keep up. So these are still just simple echo servers, but I had them do extra work. So they were doing extra data copying and checksum calculations in a loop to try and emulate some kind of business logic that you might have in your servers, and to force the system into overload. So you can see neither of them achieve their requested load because the system maxes out. So then I ran this on multi-core. I had both clients pinned to separate cores with their respective copy components. So the idea here being to take advantage of cache locality. And you can see that both of them achieve their requested load. We require in the multi-core system an explicit policy in the transmit multiplexer. So for this, I just had a simple round robin policy to ensure fairness between the client applications. Now, I'd like to try and preempt a possible question and address the fact that, like Gage said earlier, I'm human and we're pretty good at writing bugs. So it performs, but how do we know it works? Currently, we very much do trust everything, but we're working on it. We're exploring IOMMU support / SMMU support. So first off, this is measuring on actual hardware, whether it's still cheaper to copy packets as opposed to map and unmap in the IOMMU. So this might mean that we have an extra copy on the transmit path to copy in and out of pre-mapped IOMMU buffers, or it might mean we have a library in the multiplex or the driver, or even a separate component for the mapping and unmapping. We also have some preliminary drivers written in Pancake. So for those who aren't familiar with Pancake, it's a new low-level programming language under development at Trustworthy Systems, and it's designed specifically for the verification of device drivers. I understand Gunnar will be talking about that more in the next talk. And then we're going to use SMT solvers to verify individual components. So this same push-button verification technique was also used in verifying the microkit, and Gunnar will be talking about how that happened next. And then we're using Spin as a model checker to verify the communication protocols. So part of the reason why we're able to get such good performance out of the system is because we really minimize the number of system calls required and batched as much processing as we possibly could. However, you can imagine that if a component doesn't get signaled when it should have, it might never wake up and then the whole system is deadlocked. So we're using Spin to make sure that we've got this protocol correct. So to sum it all up, hopefully I've demonstrated that our simple design outperforms Linux, and these simple isolated multiplexers don't impede performance at all. However, their policies very much depend on the greater system design, how the whole system is scheduled in particular. But it is also pretty cool that we can manipulate the queue sizes to implement different policies with just a single variable rather than having explicit code in the multiplexer to do so. So we're not finished. I will be doing further investigation into the multi-core performance. There's some unexplained overheads there still. But it does bring about the question of, well, can we outperform Linux user-based frameworks as well? I know in industry they typically use frameworks such as DPDK or even the newer IOU ring to boost networking performance. So I'd like to see how our framework stacks up against theirs, particularly on higher performing hardware as well. And then, like I mentioned, we're currently working on other device classes, primarily storage, but as well as I2C, driver virtual machines even. Investigating IOMMU support and beginning the verification journey as well. Thank you.
Thank you, Lucy. We've got plenty of time for questions.
For the multi-client benchmark. Do you have a comparison to how Linux does for those?
No.
Never
I
tried?
can get one.
Because I don't know, there might be effects where Linux actually does better for those than for the single case or something. Probably not, but you know.
I
it'd be
can't
nice to-
imagine that to be the case, but it is worth verifying at least. I also, we have such significant overhead. I mean, significantly under Linux at the moment, so we have room to wiggle a little bit if the primary goal is to beat Linux.
This might be a bit of an unfair question, but you mentioned copying of things from buffers a few times. For me, copying is scary because I sit there and think, what happens with sensitive values that sit in buffers and stuff? Is there anything in place that ensures sanitization along the way by default, or are we relying on the implementer to do something above and beyond what's normally expected?
So currently we're sanitizing all the addresses that we're handing around in these ring buffers to ensure that they're in a valid location. But to answer your question about copying, we want to verify that component, and that is part of the trusted computing base. So hopefully that is helpful.
Sorry, an additional answer to the question. So this is all layer 1 networking, right? So that would usually be encrypted anyway. So you would assume that this is visible on the network, basically.
You mentioned never mapping the data from a packet into the driver's address space as an optimization. But presumably you need, the driver needs some of that information, right? It needs the headers and stuff.
Why?
Oh, well, I guess I don't know. Maybe it doesn't.
Yeah. I mean, so currently the data is mapped into the receive multiplex's address space, and that looks at the headers.
Oh, that makes sense.
Yeah.
Okay.
So the drivers do much less than Linux via this is answer.
Yeah, that makes sense.
Yeah.
That was sort of going to be my next question, was what does Linux do that...
Sorry.
What is Linux doing that you're not doing that might explain some of the difference? I mean, one thing I can think of is all the firewall stuff, which Linux is doing.
So we have no firewall, and that is a significant overhead in Linux. But the driver also has more features as well.
So I'm wondering how far we are away from actually having a system that might compete with Linux for some specialized server applications in server farms, because they go to a hell of a lot of trouble to make Linux as fast as possible. And if you're already beating that, then surely this is going to be interesting to quite a lot of people.
I hope so. I mean, Linux is full of features that aren't required in most systems or in your typical system. So I think part of the reason why we are faster is because we don't have any of that extra functionality. And the idea is to only add that as strictly necessary.
Hey Lucy, you mentioned about the SMU investigation. So if we add SMU, so that means we may have the dependency between the drivers.
Yeah.
So right now there's no framework to handle that one, so we can start the driver in some order to handle the dependency. Is there any plan for that one? Mm-hmm.
Not at this stage. That is future work. I understand that on certain hardware, the driver to use the MMU needs to have access to the data, but I'm not the person to talk to about that yet.
Any more questions?
Maybe one comment, which
Lucy forgot to make. She said this runs on the microkit at the moment, But the idea is not to be married to the microkit, so the driver framework should be pretty much independent on the underlying OS framework. And I guess in the process of adapting to all the new interfaces, we might as well just do the abstraction layer required for that. It will just be a bunch of inline functions to translate that.
Hi, I'm curious. So, are you concerned about possible feature creep in the multiplexer? Because like right now you need to parse the packets at least to understand what is the ARP request. There could be other, I don't know, IPv6 specific protocols that need to be understood so you can relay the packets. Is that a concern that you end up as a multiplexer that's doing maybe too much at some point?
Can we implement the multiplexer at layer 2 then?
Sorry, say again?
Can we implement the multiplexer at higher layers to then avoid that feature creep?
Well, I guess then you would have
so
some other component doing this.
So currently this is very much a prototype, and the idea behind layer 1 was to really try and not restrict client applications. Maybe it's a VM, maybe it wants multiple IP addresses. But if that is a concern and you're happy with one particular protocol, then it probably makes a lot more sense to have a layer 2 or layer 3 implementation, and that wouldn't be a difficult change in the code.
But I've got a different answer to this. Basically, it's just a swap in, swap out component. You're welcome to write your own multiplexer if you want to make it really complex and buggy and slow. That's up to you. It doesn't affect the rest of the world who just keep using the good ones.
Any more questions? We got 2 minutes left.
So I'm pretty sure you answered this last year, but I'd like to know if your thoughts have updated on that since then. What device drivers and things do you think should be next?
Storage.
Cool.
Yeah.
Any more? If not, I have one. And it's about the...
I can go.
It's about the suggestion of a security benefit by not mapping buffer frames into the buffer region, the bulk transit region, I forget what it's called, into the driver. And I feel like a malicious driver would be able to get that data somehow. For example, by proxying reads through itself, and by changing buffer bounds on the way out. I don't know, it just seems like drivers would... I guess, yeah, what do y'all think about
the driver can kind of do what it wants with the addresses it's handed, and it can give the NIC whatever addresses it wants to if it wants to wreak havoc. So that's part of the reason why we want to verify them.
Cool. Sweet. Yeah. All right. Any more questions? All right. We can switch it up now. Thank you, Lucy.